CADINP is the powerful scripting language at the core of the SOFiSTiK software, widely used in various fields of structural engineering. It allows engineers to create and manipulate complex models and perform advanced analysis with ease. Written in the text editor of SOFiSTiK named TEDI, the CADINP language enables users to automate repetitive tasks, customize analysis, and implement their own algorithms. With its intuitive syntax, CADINP empowers users to model and simulate structures of any size or complexity. Whether you are a seasoned engineer or a newcomer to the field, learning CADINP will provide you with a powerful toolset to tackle the most challenging structural engineering problems. Let's dive into TEDI and the CADINP language of SOFiSTiK. The word TEDI stands for the text editor, in which you can write simple basic text files or interact with various modules of SOFiSTiK. TEDI serves as both an editor and a control center that fully utilizes the CADINP language to initiate calculations and access pre- and post-processing modules of the software. To comprehend the operation of SOFiSTiK, it is essential to have a basic understanding of the structure of its programs. SOFiSTiK's programs are designed on a modular concept. All data is stored in a central database called CDB, Central Database, which serves as the primary source of data for all programs. With TEDI, the text editor, users can generate numerical input files for all SOFiSTiK program modules. In the upcoming slide, a figure will be displayed illustrating the three primary stages of structural analysis, represented by different colors along with their corresponding program module names. What can be realized from this figure is that the modules themselves don't communicate with each other, but they do so through the central database, which we abbreviate as CDB. In the text editor, we can give instructions for every program module, such as module Aqua, module SOFILOAD, or module ASE, etc. Basically to any of the available modules. Furthermore, it can be undertaken in an easy fashion, meaning that the syntax of the input is standardized and only the commands can vary. If you once learn the syntax of this language, then you will be able to write input for any of the available modules in SOFiSTiK. Allow me to provide some background information about the input language used in TEDI. The CADINP syntax utilized in the SOFiSTiK FEA product line is based on the CADINP language, which was originally developed for CAD applications in a research project back in 1976. Recognizing the benefits of the language simplicity, the founders of SOFiSTiK incorporated it into their software and continued to improve and extend its capabilities over time, necessitating deviations from the standard CADINP syntax. This ultimately led to the development of the CADINP syntax that is currently used across all SOFiSTiK modules, allowing for control of various programs and modules without the need to learn different programming languages. In TEDI, we exclusively work with the CADINP language. When we open TEDI, we are going to see the following figure or picture. First, I would like to just go through the names and the areas of the text editor because I'm going to refer to them in my presentation. In the top left corner, we will find the menu bar marked with orange color. Below that, the ribbon bar is situated, marked with cyan in the middle. In between the input area and the ribbon bar, one can find the edit bar, which is transparent in the figure. What we are going to use quite extensively is the interactive help on the right-hand side, and of course the input area in the middle, marked with yellow. On the left-hand side, we can see the module bar in purple and also the module tree in green, which is basically a tree of the modules in the current project. Below that, we can find the taskbar and also an additional interactive help line or command line marked with red color. The reason why I just showed those parts of the editor is to go through the naming convention, because I might use these terms later on. Once you have opened the TEDI application, you will see a menu labeled File at the top left corner of the screen. If you want to save your work, you can select the Save As option from the File menu. When you do this, you will notice that the default file extension for your saved work will be in a format called DAT, which stands for data. I won't go into detail about all the different menus and options in the TEDdy program because they work in a similar way to other programs you might use on your computer. What I would like to point out instead is that from the File menu in the menu bar, one can have access to the official SOFiSTiK examples. When you click on the examples under the File menu, you can open some example files already created in the installation folder. They are grouped according to the names of the modules. If you would like to get some more information about the module ASE, for example, you just simply need to open the examples folders, select the subfolder ASE, and choose the English subfolder. Then you just simply click on one of the examples, ending with the .dot extension. I encourage you very much to do so later on when you have some time and want to learn the Cadim syntax, because in these example files, apart from the pure text input, you will also find very good explanations and templates for your future projects. I think this is the best way to deepen the knowledge of CADINP and the input within the TEDdy environment. When we start to type our input in the text editor, first we need to add the command proc followed by the name of the module. We also need to provide the end statement or the end command into our last input line that closes the module. In between the module name and the end statement, we are going to also enter a heading in the form of the command head. Whatever is typed right after the head statement will appear as a heading in the report browser when look at the output of the current module. Therefore, it is useful and suggestible to add a full explanatory sentence like material definition of a tunnel or something similar. The so-called records will follow the head command and finish before the end statement. One record can have several items, and the items can have multiple values assigned to them. By the way, sometimes I'm going to use the name command instead of the record, and maybe instead of the item you are going to hear parameter from me. In those cases, I'm referring to the same things, just with different terminology. I will try my best and always say record and item, but if I miss it, sorry for that. Now I would like to demonstrate the syntax of the language through a simple example. As you can see, the first module that is called in every .dot file is the aqua module, at least in most of the cases, which module stands for the definition of the materials and the cross-sections in the project. After the head statement, the first few records appear. Please pay attention to the different colors in one command line. With dark blue color, the records are shown. A light blue color will indicate the items of the record, and the values are in black. The input consists of lines. Each line contains up to maximum 255 characters and corresponds to one line on the screen. More than one record can be typed in the same line. In this case, however, the records must be separated by semicolon. The semicolon needs not to be between separation characters. This feature cannot be applied to the input of text lines, so for example to the head statement. Each record occupies one input line. The record name can be omitted when the record is of the same type as the preceding one. A record can start at any position in a line. If we look at the syntax of the current command line of record conc, we can see that between the record name and the items and their values there are white spaces. At the moment there is only one white space, but of course more than one character of white space is allowed. On the other hand, fewer than one character of space is not allowed, since then the software will not recognize your input as a command. My recommendation is that in order to make the code more readable, use a separate line for each and every record. The input of the commands are case insensitive, meaning it doesn't matter if they are entered with capitals or lowercase characters. It is possible to convert the text from capitals to lowercase characters or vice versa with the Ctrl+Q+L keyboard combination. Please notice that the name of the records cannot be longer than 4 characters. This also applies to the items. An item can store different types of values. Most of the cases we are assigning integers or decimal numbers or sometimes entering an expression. In other cases, just entering characters or strings of characters. It can sometimes be noticed in the input of the official example files or other .dat files received from other users that the name of the items are omitted, and after the record name only the values are followed. This is allowed in the Cadim syntax, but only if the order of the given values correspond to the original order of the items in the record. What does it mean in practice? In other words, it means that without the item name specified, the software will use the first value and assign it to the first item of the record, then the second value to the second item, and so on and so forth. This type of input could be faster because no need to enter the many item names. But its disadvantage is that if you miss the order of the items, a different or unwanted value will be used by the software, not to mention that the code is less readable for a human being. The items with their values can be selected by the mouse and freely move to a different position in the command line if it helps rationalize the items. The head and the end statements help the software to understand where the instructions or records start and where they end in the specific module. It is possible to enter the record either in English or in German. The software will automatically recognize which language you are working with from the typed head and the end statement. The head and the end statement pair indicates forthcoming English records. On the other hand, the Kopf and Ende pair will allow entering the records in German. Changing between the languages is possible via the Ctrl+Q+T keyboard combination, where Q+T stands for a quick translation. Comments are added with the purpose of making the text input easier for humans to understand and to provide short explanations or annotation. The special characters such as the $, the exclamation point, or the double backslash turns the rest of the command line into a comment which will be ignored by the program. All these comment operators should be separated from the comment itself and also from the input data in the same line with a separation character. Within a +prog line, only the $sign character is allowed as a comment, and it must be separated by white spaces. A double $sign means that the input record is continued in the next line. A separation character must be entered right before the double $sign. Thus, it is not possible to write expressions or a list of values extending more than one line. Of course, at the very beginning of your Cadim journey, when you familiarize yourself with the text input, you don't know anything about the names of the available records, what they are doing, and what items are possible to enter after them. Don't worry, you just need to ask for some help. But how? When the cursor is standing on one character in a command line, you just need to press the F1 button and then an interactive help will open. The interactive help can be docked either on the left or on the right hand side of the screen. If you call for the interactive help, you will experience that the manual of the current module you are working in at the moment will be opened automatically, and also the command that you tried to enter will be presented in an interactive PDF. Certainly, this manual can also be found in the installation folder of the software for every module. When you want to understand the record, please always start with reading its title, because it gives some general information about the record and what it does or undertakes. In this case, with the record norm, for example, we can define the default design code for our project. A table can be found below the record's title, which contains 4 columns. The first column displays the name of the record's items. The second column provides a brief description of the items. The third column shows the units of the measurement for the items, along with their default values in parentheses, if applicable. In this instance, the item norm has several items, such as DC and NDC, and then count and cut, and so on and so forth. For the item DC, the required unit from the user is a literal whose default value is EN. When no input is entered after the item, the software will automatically consider the value of item DC as EN, meaning Euronorm, since this is the default. However, one can also see that for some other items, such as G, a different unit is necessary. The item G stands for the gravity acceleration, and its unit is given in meter per second square. If someone scrolls down in the table of the record, which I always encourage to do, a more detailed explanation of the items will be found. In the small area for the description column, it is not possible to enter all the necessary and descriptive information. Hence, this information is provided below the table. That is why I'm always asking everybody to scroll down and below the table read the item's description, when a proper description fails in the table of the command. Another interactive help for the user to be oriented well and also to know the available item names of a record is presented at the bottom of the screen in the so-called help line. If you look at this line with caution, you will realize that it displays the current record name conc and afterwards the available items such as NO, type, FCN, FC, FCT, FCTK, and so on and so forth. There are a lot of items available for this particular record. Until now I have covered the first two columns of a record, namely the item and the description. Now I would like to talk a bit about the units of the items shown in the third column of the explanation table of a record in the interactive manual. If you don't see any type of parentheses around the unit, meaning normal parentheses or square brackets, it means that this unit cannot be changed. Its value must be entered in the shown unit. Why? What is the reason behind this? When a unit is not changeable, it is normally used for classification. For example, in the case of a concrete material, the item FCN, the value that can be entered is for the classification of the concrete. That is why its unit is in Newton per square millimeter. In the Euronorm family, we got used to the Newton per square millimeter unit for classification of a concrete. If the value of an item is not used for a classification, it can be given in a different and more comfortable unit if it is necessary. Please be aware that any given unit differ from the default one will automatically be converted to the standard SI units for the time of the processing, such as kilonewton, meter, second, and so on. One can see that sometimes around the units there are square brackets, and in the subscription or as an index a green number can be seen. This means that it is an implicit unit and it can be changed by the user. The implicit unit can be best explained with the help of the units dialog box in the system information in SSD. At the top of the units dialog box you can see a few predefined unit sets, or one can say unit environments, based upon the chosen code. According to the selected norm or standard, the software tries to suggest what is the best suitable unit system for the project. The predefined unit sets are numbered from 0 to 9. One can disagree with the preselection and simply select any other unit environment. The implicit unit change means that although the unit environment is already set to a specific value, it is still possible to change only one entry from the whole unit set, such as the length or the area, etc. Within a module, with the help of text input, the command unit, followed by a number from 0 to 9, will set the unit environment, as it can be done in the same way graphically in the units dialog box. But what if I want to change a unit implicitly in the Cadim language? Well, next to the default unit, in brackets, a small number can be found as a subscription. This number can be referred to in the current module by entering the record unit, followed by the number that was presented in the bottom right corner of the unit's brackets, and followed by the desired unit. However, be careful, since this change also means that every unit that is marked with the same number in the subscription will be changed. The numbers presented as a subscription of the brackets can be reviewed either in SSD in the unit dialog box, or they are also presented in the cdbase.chm file. This very special file can be opened from the installation folder of the current version of SOFiSTiK. After having opened it, a help file about the content of the CDB itself and its properties will be shown. This file is easy to search through for a specific ID number that controls implicit units such as geometric lengths in the model or deformations, etc. This slide shows the implicit units, for example, in the cdbase.chm file. And this is just a closer look of the implicit units. Finally, let's see how one unit can be explicitly changed in a particular module with text input. An explicit unit change means that the unit of one value needs to be changed. In this case, simply the desired unit must be entered in square brackets, and only the unit of the particular value will be changed explicitly. That's why it is called explicit unit change. In the following slides, I would like to elaborate the positioning of the items in the record, as it is an important aspect of the Cadim syntax. Generally speaking, the items are processed one after the other in one record. In this case, the name of the items need not to be typed. By entering the name of an item inside the record, you can provide the value for that item regardless of its position. So you can change the position of the items together with their values anywhere in the record until you make sure the name of the item is typed. The default value of one item can be given with a minus symbol. In this slide, a simple example has been created in which all the items will be assigned with a default value of 3.0 unless explicitly specified otherwise. For instance, let's consider a record consisting of the items I1, I2, I3, I4 and I5. In this case, the following input lines would be equivalent. By specifying an item in a record, the preceding position or positions can be omitted. Or in other words, the item I2 and I3 can be skipped by specifying I4 right after item I1. Please notice that in the last command line, the original order of the item has changed. However, entering the name of the item such as I4, I1 and I5 is mandatory in this case. By specifying a record name followed only by the items, the preset order of the input values can be changed. It means you can enter only the items one after another in the order you want without assigning any value to them. In the forthcoming line, however, it is sufficient to provide only the values, but in the order of the previously given items. This is called a table definition. Please be advised that the input line with the values only mustn't contain any item or record name. A table definition remains valid until a new record name is entered or the same record name is repeated. Inside the table, the positioning is still possible even for those items not defined in the table definition. Within the table header, the default value or values of the record can be reset to a desired value by using an equal sign followed by the item name and the new default value without any further separation character. Please notice in the example shown that the reset default value of item 5 can still be overwritten by an explicit input value. Using table definitions can be an effective solution to avoid ambiguity in the input language. In case there is a literal value such as GRP, which is also a valid record name, The problem can be resolved by changing the sequence and/or assigning default values without having to use quotation marks or repeating input lines. This approach is particularly useful in handling cases where there are multiple items with similar names or values. By defining tables, it is possible to provide clear and concise input, which ultimately leads to improved efficiency and accuracy in the software's processing of the input data. A series of records can be created automatically without using any looping technique. This quite practical type of instruction for automatic record generation can be given in one single record without the need of repetition. When generating the record, the value of the relevant item must be enclosed within parentheses. The given value within the brackets must be separated by separation characters. There are two types of generation instructions. The primary automatic generation instruction with a start value, end value, and increment, and the secondary generation instruction with start value and increment. In this slide, a simple use case can be seen for generating multiple nodes. The primary generation instruction specifies the number of the individual records to be generated. It can be used only once per record, however, in any position, or better to say, item in the record. The corresponding secondary generation instruction can be defined for every item. The generation of literals is also possible. The increment is then also considered as a literal, but may contain only numbers. The increment can also be negative. Please notice the lane number in the first bracket. So the primary generation instruction contains literals as well as numbers. Only the number after the dot symbol can be incremented. The AX prefix remains constant. Please also remark that the secondary generation instruction occurs and controls multiple items. A list of values can be given instead of generating a loop structure. This can be undertaken in a series of values separated by commas. For example, value 1, value 2, value 3, value 4, or 1, 7, 9. A list of values mustn't contain any separation characters and cannot be spread across multiple lines. When several lists of values are defined within a single record, their number of values must match not only with each other at the items, but also with any other defined primary generation. Please see in the below input that the numbers of the steel material must have a unique number, different from the number of the concrete. The maximum number of values per list is limited by an internal amount of memory. A list of 25 values is usually possible. A list of values can also be built up by fixed literals, such as in the case of item class in commands T. Combination of numbers and literals or a list of freely defined literals are, however, not allowed. In the CADINP language, it is also possible to declare and initialize variables. Two major types of variables can be distinguished in SOFiSTiK. One of them is the so-called local variable, and those can be defined with the record let, and also a global variable for which the command sto can be used. What is the difference between the two? The scope of the local variable is only within the module that it had been generated, whereas a global variable will be available for further usage throughout all the modules, not just in the particular one in which it had been defined. Now let's see how to define the variables in practice. A combination of the hash, or sometimes it is called the pound symbol, shall be used with the desired variable name for this purpose. The variable name can be a maximum of 16 characters. The variable name cannot contain special characters and, of course, white spaces. The variable name should start with a letter from A to Z or with the underscore character. Remember, the variable names are also case insensitive, just like any other input in the CADINP language. I've just created some examples to demonstrate the definition of local variables starting with the let command. The first definition is the simplest one, namely with the let hash a 5.1. As a result of this input, the variable a gets a single value of 5.1. If after the constant no unit is given, or in square brackets a minus sign is entered, it means the variable doesn't hold any unit. In the next line, the definition was undertaken with the let hash b 5.1 millimeter in brackets, which assigns the millimeter unit to variable b. It is an implicit unit definition, and in this case the variable b gets a single value of 5.1 millimeter. The unit of the variable will also be taken into account in this case. Please be aware that strange or unwanted results might occur if a variable is defined with a unit and used in an expression together with other variables without any unit. So, a good practice is to either define every variable in the project with units or all of them without any. In the next line, the instruction let hash 10 456 generates variable 10 to which the value 4 is assigned, followed by variable 11 to which 5 is assigned, and variable 12 to which 6 is assigned. One can create a variable with a string constant as well, such as in the next command line. The instruction let hash text and the string test in apostrophes will generate the variable text that holds the string constant test. One additional side note is that instead of the apostrophes, single quotation marks can also be used. It is also possible to define one-dimensional arrays. For example, the command let hash c 4,5,6 creates a vector c with the values of 4, 5 and 6. The indexing of the elements in the vector always starts from 0. Unfortunately, it is not possible to create multidimensional arrays in the Cadim language. When one defines a vector like let hash d in bracket 0 space 7, it means that the 0th element of the vector shall be equal with 7. If you define a vector with the command let hash e 2 in brackets space 9, then the second element will be equal to 9, and the 0th and the first element will be 0, but the second 9. In other words, the vector will be filled with zeros prior to the given value at the second position. Very similarly, if one defines a vector with the command let hash f 0 in brackets plus 1 space 8, it means that the zeroth value plus 1, so the value of the element in the first position will be equal to 8, and the preceding element or elements will be 0. After the definition of the variables, they can be printed as output to the report. To do so, you must enter the record PRT hash, followed by the name of the variable. Of course, you need to run the module itself in which the variable were prescribed. After having run the module and opened its report, it seems that nothing happened at the first glance. However, if open a chapter by clicking on it with your right mouse button, the input data and also the output will be presented, and all the values that we entered and then processed are displayed. It is also possible to create a different type of variable which we can call a literal or string variable, and which needs to be generated with the hash-defined record followed by the name of the variable and an equal symbol and a literal or string on the right-hand side of the assignment. Like so, hash define a3 equals text. It is also possible to assign a number constant, for example 12, to variable created in this manner. But you need to be aware that it will be stored as a literal. The hash define variable can be defined at any position in the dot file, even outside of a module. In contrast to that, The let and store variables must always be created in a module. Also, it is important to mention that the program evaluates all the hash-defined variables first and the let and store variables only after that. So one can say that the hash-defined variable has precedence over the let and store variables. Some important rules to comply with when defining a text variable are as follows. The value assigned to the text block can be a text of any length. Parameters within an assignment are not evaluated until the replacement. A redefinition of an assignment is possible. A parameter in the input data or in a block can be referred to by using the syntax $, followed by name in parentheses without any white space. Blank spaces are not allowed between the $ symbol and the parenthesis symbol. The name is case insensitive, meaning upper lowercase letters have no influence. There are default parameters, namely $, and name in brackets, containing the primary name of the output file, and $, project in brackets, containing the name of the project. These can be helpful, especially when using the apply or the sys commands, as we will see later on in this video. The different behavior of the text block can also be realized from the way the output of this variable A3 must be requested. It is a little bit different from what we learned at the let and store variables. Instead of the PRT command, you need to use the TXE command, which stands for a text request at the end of the report. In other words, the value of this variable A3 will be printed at the end of the report. If it is better to be printed at the beginning, then the TXB command must be used. So TXE refers to the text at the end, and TXB refers to the text at the beginning. To be able to read out the value from a text variable, the name of the variable must be placed in parentheses with a preceding $, without any space in between. If you hover over your mouse over the variable name, it shows the current stored value of the variable. After having run the module and opened its report, it displays the value, in this case the character sequence text, at the end of the module's output. Let's see an example which starts right away with the definition of variables outside of the module, such as hash-defined lengths, hash-defined width, hash-defined height, and hash-defined plate. Please notice that for the last text variable plate, multiple values with white spaces in between were used, like 500 space 200 space 100 space 800. But how to use this type of variable in module Aqua? As I mentioned previously, to invoke the value of a hash-defined variable, you must use the $, followed by the name of the variable in brackets. In this example, for the standard rectangular cross-section, which is numbered with 1, the value of item h will be equal to the variable height, the value of item b with the variable width. Now please pay attention to the standard rectangular cross-section number 2, starting with the record srec NO2. The value of item h will be equal to variable plate, but it contains multiple strings with white space in between. What's going to happen in this case? Actually, the hash-defined plate variable will be pasted as a strip of text. So, to item h, the value of 800 will be assigned. To the next item b, which is not typed, but can be figured out from the help line below, the second value from the plate variable will be assigned. To item ho, the value 100, and to item bo, the last value 800. This is what I referred to previously as omitting the name of the items in the command, as long as you keep the order of the items. In this slide, we can see once more what I had explained in the previous slide by substituting the parameters. With hashDefine, you can also create a block of text in multiple lines with many records and items. It must start with the hashDefine command, followed by a name of the text block. After the hashDefine and the variable name, multi-line text or records could be typed. This text block type of definition must be closed with the #enddef command. There isn't any restriction regarding the number of lines used. The advantage of this type of definition is that it can be invoked multiple times throughout many modules as you paste the text block again. Pasting the text block is possible with the #include command, followed by the name of the text block. You will find some relevant use cases of this variable definition throughout the official example files. It really saves a lot of time and typing effort. You create the text block once, but paste it as many times as necessary. Now you can see in the report after having run the template module that the entered text will be printed 2 times, since the text block variable was inserted 2 times as well. Please note that the name of the text block can be omitted after the #enddef command. In other words, a simple #enddef command is enough to close the definition. Now let's see the same type of variable in a second example presented on the screen. In the similar fashion, I have now created a text block with the command #define sect. However, this time instead of entering a simple text, I typed records and items and corresponding values, which I was going to use multiple times in the coming Aqua module for the definition of many cross-sections. As you can see, there is a normal let variable being defined in the text block variable, whose value will only be provided before the text block is pasted into the module. And the nice thing is that it can be repeated multiple times by assigning different values to the let variable. Whenever the text block is inserted, the record polyopz followed by the word1 and word2 command lines will be copied in, where record word stands for the generation of the vertex points of the cross-section, and record polyopz sets a symmetrical cross-section to the local z-axis. Just before pasting the sect text block below the generation of the cross-section with command sect, the values for the variable #1, #2 and #3 will be invoked from the statement let #1 0.6, 0.20, 0.60 respectively. With very little effort, multiple cross-sections can be created in one particular Aqua module. After having run the Aqua module, its report will display 3 cross-sections with numbers 1 and 2 and 3 as per the input, as we expected. I would like to still go on with another example demonstrating the capabilities of the #define command, because it really has some more potential. Let's suppose that the generation of the model, such as creating the materials, cross-sections and geometry, has occurred in SOFiStiK, which way of modeling I support always. After having exported the model from SOFiStiK to the database, you can continue working on it and perform the processing and post-processing of the available data in TEDI. For this purpose, the #define project command can be used. In the CADINP environment, we just need to refer to the CDB by entering its name after a preceding #define project command. The CDB doesn't even need to be stored in the same directory as the .dot file from which it is invoked. In that case, a proper path of the CDB must be typed after the equal sign of the #define project command. In other words, what you can achieve with the help of this #define project equal command is to continue working on the model after having exported it from SOFiStiK to the CDB, which utilizes all the advantages of both of the graphical and the text-based workflow. A more complex geometry of the model can be undertaken in a graphical way in SOFiStiK, followed by a much faster parameterized input of the processing and post-processing in TEDI. Take the following example in which spring elements should be created along half a circle at every 30 degrees. The springs will be created with the help of a loop and two let variables, namely with hash number 1 and hash number 2. In the CADINP language, the loop is always initialized with the command loop and ends with the statement end loop. The number of repetition can be set with a number followed by the loop command. In the body of the loop, multiple statements can be entered. To generate the nodes where the spring elements will be situated, the command node needs to be used. Then the spring elements must be created taking care of their orientation. Hence, there will be two records given in the body of the loop apart from the incrementing commands of the variables. The number of the node needs to be added at item NO of record node, whereas the items x and y are for the coordinates of the node in the global coordinate system. The spring elements also have to have a number defined with the item NO of command spree. The beginning point of the spring is prescribed with the item NA, and if no value is given for the next item, which is NE, the spring will be created without a second node, meaning it will be a spring with a unit length whose direction is aligned with the items dx and dy. The item CP stands for the stiffness constant of the spring. Let's go through the first loop and crunch the numbers together. In the first go, the value of number 1 equals to 1 and number 2 is with 0. Therefore, a node with number 1 will be generated at 1 meter, since cosine 0 is equal to 1, which will be used at item x, and the y-coordinate will be 0 since sine 0 equals to 0. So actually, a node will be created at x equal 1 and y equals 0 meter. Then the value of hash number 1 will be incremented with 1, and hash number 2 will be incremented with 30 degrees. Then starts the second loop in which a new node will be created with a number of 2 and a new spring will be defined at the node aligned according to the cosine 30 and sine 30 degrees. Then the loop will be repeated 5 more times. When someone looks at the results of the loop input in the report browser, which was generated with the help of an interactive graphic under which the module wing was working, it can be found that 7 springs were really generated at every 30 degrees and their direction was aligned to the center of the half circle. If the number of repetition is known before the execution of the loop, a so-called for loop is used in other programming languages. Entering a number after the loop command has the same effect in CADINP. However, if the number of the repetition is unknown, a condition is going to be tested at the end of the loop. This type of loop is called do-while loop or repeat until loop in other programming languages. The next example tries to demonstrate this. The aim of the example is the same, namely, spring elements should be created along a half circle at every 30 degrees. The only difference in the input compared with the one in the previous example is that I entered a condition at the end of the loop as end loop #2 smaller or equal 180 and deleted the explicit number after the loop command at the beginning of the loop. If the expression at the end of the loop is evaluated to false, then the loop will be terminated. When an expression is evaluated to 0 or negative number, it is considered as false. In the following example file, I would like to show that there is also a way to loop through the elements of a vector. First of all, a vector can be created by defining a let or store variable, like in this case with let #a, followed by numbers separated with commas, which are then going to be stored as the elements of the vector. If you want to perform the body of a loop as many times as many elements the vector has, you need to enter the identifier of the vector, but without the hash symbol. What the loop #1a command means in this example is that the loop will be executed as many times as many elements the array has. Please note that the hash symbol was disregarded if the number of an array had to be used. In this case, the array A has 6 elements, so the loop will be repeated 6 times. If we try to follow along the substituted values of the items, we will find that in the first repetition the value of item NO of command node will be 0 plus 1 equals to 1, since the first index of the array is 0. The item X will be evaluated to 10, since this is the first element of the array, which was called by the input hash A, hash 1 in brackets. Now it can be seen that by giving the index number in brackets next to the array name without any white space in between, it will invoke the corresponding element of the array. In the second execution of the body of the loop, 22, the second value of the array will be substituted to item X, while item X will be 1 plus 1 equals to 2, and so on. In this way, the loop will go through every value of the vector. Reviewing the result of the input in the report browser, it can really be seen that the string element has been created at x equals to 10 meter, 22 meter, 34, 55, 76 and 83 meter. So far so good, but can we execute the loops based upon condition? In other words, can we insert any condition in between the loops? Yes, it is possible via the if statement. To implement conditional logic in CADINP, you can use the if statement. This statement allows you to create conditional blocks based on certain expressions. Unlike other programming languages, you cannot use the goto statement for jumps in CADINP. To create a conditional block, start with the if command followed by the expression you want to evaluate. The block should be closed with the endif command with no white space between and if. You can use the elseif and else commands to set up branching within the block. When the expression following the if statement is greater than 0, the conditional block will be executed. Otherwise, if the expression evaluates to 0 or negative, the else branch will be executed if specified. To compare text in the software, you can use logical expressions with the double equal sign and exclamation point equal sign operators only. It is important to note that the comparison is case sensitive and the complete string on both sides of the operator is considered, so parentheses are not allowed as they are part of the strings. It is important to be careful when evaluating and comparing floating point numbers, as they cannot be represented exactly within a computer in most cases. Therefore, when using the double equal or exclamation point equal sign operators to compare fractional values, a tolerance should be applied. To avoid misinterpretation, it is recommended to use parentheses to evaluate the condition after the if statement. This is because the precedence of the operators follow the rules of mathematics, but the logical operators have the same precedence as the arithmetic operators. It is worth noting that CADINP doesn't have a built-in case construction, unlike other advanced programming languages. However, it is possible to generate a case construction by utilizing a sequence of additional else-if statements. In the following example file, I try to expose the behavior of the if statement. After having defined the materials, the geometry of the model shall be given in module SOFiMesh-C. Based on the value of the height of the retaining wall, which is given in variable sto_h, the width of the footing of the retaining wall will be different on the left and on the right side, respectively. The structural points number 4 and 5 under the if statement will be created with the fixed x and y values only if the variable #h is smaller than 2 meters. Or else, if the variable #h is greater than 4 meters, then the x and y items will be created depending on the values of variables #r and #l given in the statements under the else-if branch. When the value of hash h is between 2 and 4 meters, then the statements under the else branch will be executed. Moving forward, a very interesting command line will be presented very soon, which is called apply. To better understand the apply statement itself, I would like to broaden the knowledge of the #include command first. Previously in this session, the #include command was mentioned when the possibility of the inclusion of the text block variable was explained. It is also possible with the #include statement to invoke external files, not just text blocks created in the same .file. The #include command, followed by the name of the external file, will copy content of the external file line by line into the source.file. It is very similar to the so-called header files in the C programming language. The advantage of this procedure is that when the same input needs to be used multiple times, or the content of the external file is so long that it would make the readability difficult in the parent file which invokes it. The external file can be called simply by its name if it is stored in the same folder as the source. Otherwise, it can also be invoked through a given path. One can also copy the content of the invoked file into the working dot via the insert all include files command, which can be found under the Home tab at the Additional section in CADINP. The insertion of the content will clearly be indicated by the program with an opening !include line and a closing !incend, which stands for include end. This method makes the debugging of a .file easier when too many #include files were used in the master .file. The apply command is very similar to the #include. With it, a file can also be included anywhere between two blocks in the input dataset, but not inside a module. This file should contain one or more module calls starting with +prog and then the name of the module. While with the #include, the data are inserted before the calculation into the dataset, the apply command is executed during the computation, i.e., the data can be generated during a calculation and thereafter be inserted at the right place. Additionally, the apply statement can be controlled with a plus or minus sign. That means with +apply, the command is executed. With -apply, it will be skipped. A typical example for the use of the apply command is the program CSM, Construction Stage Manager. Using the CSM module, a file named $name in brackets _csm ... is created in the project folder, in which a recipe is being generated by module CSM how to perform the ASE and AQB runs one after another, but it shall not be run unless there is a +apply statement preceding it. In other words, the _csm ... file is invoked with apply into the calculation. Sometimes the content of the _csm ... file is quite extensive with lots of stages inside. By entering -apply in front of the csm ... enables the user to first review the extensive input of the file and only run everything according to the needs. In the presented example called master.file, one can see several #include statements referring to the predefined .files from the project folder. In between those statements, two apply commands can be found with plus or minus sign preceding them and a .file succeeding them. The one with the plus sign will be invoked to the master.file, whereas the one with minus sign will be omitted. If I want, I can execute the master file once with choosing the SOFiMesh-C module for the generation of the modular geometry, and once with the SOFiMesh-A module for the same purpose. Please notice the advantage of the apply command, namely, one can control which dot file to be run with the plus and minus signs, which can be activated or deactivated in the task tree on the left-hand side of the text editor. In contrast to that, in case of the hash include statements, the only way to regulate their behavior in the master file is commenting out the statements. Now let's continue with the operating system commands, or the sys command as one might also call them. With these commands, it is possible to integrate Windows shell commands in the input file or in the analysis. The parameter substitution is also active in these sys command lines. What does it mean? It means that the character string $, name in brackets will be replaced by the name of the input or output file. Similarly, the $project string will be substituted with the name of the project. Let's see some examples for better understanding. The +sysdel $project.$d1 command shall delete the file from the project folder whose extension is $d1, which holds a part of the stiffness matrix. Of course, any other extensions and name can be given. A common use case of the sys command when you work in TEDI is when the report file of one specific module needs to be stored in the project folder with a specific name referring to the model that had been calculated. In this case, the following two sys command lines can be used. The first one deletes the report file called 01-materials plus cross-section.plb if there is any in the project folder with this name, and then via the second input line, the current report browser file, the plb file, will be renamed to the specific 01-materials plus cross-section.plb, which will contain the information of the lastly run module. These two sys command lines enable the user to create a report file for every module in the project respectively. Otherwise, which is the default case in the TEDI environment, when one or more modules are being executed, the content of the last run will be printed to the report file, whose name is $project_plb, and the output of the previously run modules will be lost. There are other sys commands as well, such as syscopy and syssps. The latter one will run the sps.exe file from the installation folder of SOFiSTiK, with which a batch type of execution of the files is possible. The syscopy, on the other hand, will copy the file from one location to another. As we get used to the usage of the plus and minus signs at the apply command, we can also use them for the sys commands. A plus sign will execute the specific sys command, whereas the minus sign will deactivate the execution. One more additional important hint. Within a sys command line, no comments are allowed at all. The common $, exclamation point, or / characters cannot be used. In order to organize the output a bit better in the report browser, as well as to add some explanation, the txe and txb instruction can be used with the let and sto variables. These variables can be printed with a certain spacing and decimal precision if it is necessary, even if they are part of an expression. With txb, the variables will be printed at the very top of the module's report, whereas with the txe at the very end. If you are familiar with the HTML language a bit, you know that instead of commands or records, the so-called tags are used in it. Most of the cases there is an opening and a closing tag, and the text to be presented needs to be entered in between those. This is also allowed in any of the modules with the text beginning tag and text closing tag. In the similar fashion, other HTML tags can also be used, like printing the text in bold, the B opening tag and the B closing tag, in italics with the I opening tag, I closing tags, and so on and so forth.